Hello and welcome to another live session for the online course. The floor is open for your questions.
All right, so our first question is from Zane, who is on with us live, who says, I'm very curious about the Aristarchus crater on the moon with its unusually large albedo and bluish sparkle as seen from a telescope. Is it possible you could explain the cause of
Um, I mean, in general terms, I'm not a geologist, so this will be sort of fairly high level in general. I got my sort of introduction to lunar geology because there's this really cool thing that NASA sends around to educators. It's the Lunar Sample Disk, and it's kind of nice because it has small samples from each of the Apollo landing sites embedded in a perspex disk, so it's sort of indestructible, and you can hand it around class, and it's kind of cool to see kids in the class, none of whom were born when the Apollo landings happened, see these actual samples from the moon. And when you see these samples, one of the lunar landings, and I can't remember what the number was, is in an upland region and in a cratered upland region, which has these quartz-like deposits. So there are sort of pale quartz-like lunar deposits that are exposed. There are subterranean layers exposed in a crater, moon with no atmosphere that really doesn't change over time. And that's pretty much the geology of the Aristarchus crater. It's fairly light quartz-like material. It's pulverized, by micrometeorite impacts that affect the surface few centimeters over time, and so it's sort of pulverized into sort of fine, glittery, pale sand. And seen from a distance and seen over a large area, it makes quite a striking feature on the moon. So that crater really does pop.
this? Right, excuse me, Cecil, who's on with us now live, asks, what is the cause of temperature variation in dark matter in our solar system and dark matter between galaxies? So it sounds like it means the space, like what it's caused the temperature variation between, within our solar system and between our solar
Right.
systems.
So dark matter itself doesn't really have a temperature. It's first of all, we don't know exactly what it is. Dark matter is almost certainly a fundamental particle, um, and so dark matter is a particle that has a mass, has an energy. It doesn't really have a particular temperature. The temperature of the universe, of course, in on the large scales where most of the dark matter is just below 3 Kelvin from the microwave background. So matter that was in equilibrium or interacting with the microwave radiation um, would take the temperature of the background of the universe. However, dark matter, of course, does not interact with radiation. That's part of the point. That's what makes it dark. It has very weak uh, coupling to electromagnetic radiation, and so that's another reason why dark matter doesn't really make sense to think of it as having a temperature, because it doesn't couple to thermal radiation and therefore doesn't equilibrate with the thermal bath of radiation that the universe is in. Um, However, dark matter does cluster, of course, and it does, the baryons, of course, follow the dark matter because it sets the potential well, since it's 6 times the amount of the normal matter. So where dark matter concentrations are largest, often the temperature of normal matter is highest because that matter has come together, collided, created stars, gas is heated up, and so on. And the dark matter serves a role in that because it facilitates the clustering of matter, and it sort of stirs up the matter and makes it even hotter. Um, so there's no direct implication of dark matter with temperature, but it correlates with the temperature of the normal matter that tends to follow its gravity.
All right, the next question is from a live viewer who asks, with the more recent discoveries in astronomy, um, what's been more probable? What's the probability of something having happened before the Big Bang?
Well, the issue of talking about the time before the Big Bang is still a matter of very active speculation in cosmology. So to be very clear, the Big Bang model, which has enormously impressive observational support, especially with observations of the microwave background in the last decade, uh, is a description, a physical description of the universe from a state of essentially infinite temperature, density, and zero size. Now, that is a state that cannot be understood through normal physics because it alludes to a time when we would have to have a quantum theory of gravity, which we don't have. So in a very simple sense, the Big Bang model runs out of steam or becomes indeterminate at the origin. And because of that, it therefore also makes no sense to talk about what came before the Big Bang or what happened before the Big Bang. So all talk of before the Big Bang or precursor states is pure speculation. Important to remember that because people write long articles and in reasonable journals, Scientific American and popular science journals, and academic articles too. But it's important to remember that it is pure speculation because we do not have a physical theory to properly describe the precursor state of the Big Bang. Those theories, such as they are, involve guesses or best speculation as to what quantum gravity theory might be like. Some of them depend on string theory. They often involve quantum genesis, where there are other quantum states alongside the Big Bang, possibly preceding it, and so on, in a sort of almost timeless state that before time switches on in our universe. But they are absolutely unconfirmed by observation.
All right, the next question is, can you give an update on planetary findings of the Kepler mission? And in particular, focusing on like what are current findings of Earth mass planets?
So Kepler is in the twilight of its time as a mission. It lost some of its pointing capability. It lived the appropriate amount of time, actually longer than it was planned to run. It had a 5-year core mission, and it's now in an extended phase where its pointing is limited enough that it can't do its typical transit work, but it can do broader swaths of sky and lower sensitivity work. So it's continuing to do interesting things. But people are still crunching through the Kepler data because you need to look at it with a fine-tooth comb, especially to pick out the smallest transits. And that sensitivity limit is around a Mars mass. So Kepler has found a significant number of planets that are sub-Earths or Mars-like planets. I think the number of Earth-like planets that's within a factor of 2 of the Earth is around about 1,000. The number of sub-Earths is a lot smaller because it runs out of sensitivity, so it's probably about 100 or so. Super-Earths is another 1,000. Mini Neptunes and Uranus type things, another 1,000. And then the numbers start to decline towards Jupiter mass. And the total of adding up all those categories or bins of mass, or size rather, because that's what Kepler finds, is about 5,000. So just over 5,000 candidate. They call them candidate exoplanets, but in sampling studies to see what the reliability of those candidates are, it's about 95%. So even though they are cautious and call that large number of over 5,000 candidates, almost all of them will be confirmed and are real. So that's the haul of Kepler. The most exciting aspects now are to, of course, nail down the number of habitable Earth-like planets, not just Earth size, but also in the habitable zones of their various stars. And that final number probably will be published sometime in the next year. There's a guess at it already a few years ago, but the final number will come soon. The other thing people are trying to do is sift through the Kepler data to see if they can detect the first exomoon. That's relevant because in astrobiology, habitable worlds are likely to include the moons of giant planets that are quite far from their stars, as well as Earth-like planets that are in the Goldilocks zone where water can be liquid on the surface. We have such objects in our solar system. We have Europa, which has water under an icy cap, and probably another 6, 7, maybe even 8 moons of giant planets that have liquid water under the surface. So detecting exomoons, that is moons around planets around other stars, would be very exciting. See, obviously extremely difficult because the largest moon in the solar system is about or slightly larger than the mass of Mercury. The Mercury mass is about where Kepler runs out of steam. So it's at the limit of detection. So it's a blip on top of a blip, basically, in terms of finding the shadowing caused by a moon around a planet, around a star. But there are a couple of teams working on this, and they think they might succeed in the total Kepler database.
All right, the next question from a live viewer is, what's the best way to stay up to date on Kepler findings?
NASA's very good about this now. NASA's not all missions are equally well maintained, um, but Kepler's run out of the Jet Propulsion Lab in Pasadena, and so NASA centers sort of have their own web pages and run their own web shows, if you like, for their various missions. And so JPL has always been one of the best NASA sites as far as their web pages. So the Kepler mission has extremely good and well and current data. And it's the data itself. You can download Excel spreadsheets of the planets that it's found with their properties, and you can, if you want to use them in a class, if you teach, or if you just want to explore the data yourself. They also have a visualization option. So NASA has developed some sort of virtual reality type software that works in a web browser that lets you explore, in an interactive way, these many habitable worlds, and it shows the information as you explore in this sort of three-dimensional space online. So you'll find that links to that on the NASA JPL Kepler site. So it's a pretty cool website.
Thanks. The next question is from Samir, who's on with us live, who asks, being a hobbyist, I want to understand and know what is the origin of gravity, or are we able to explain it? I know of Einstein's theory of space-time curvature, but I want to know the origin of gravity.
So, I mean, the conception of gravity has changed over the years, over the centuries. The Newtonian conception of gravity associates it simply, directly, and uniquely with mass. So gravity is a property of mass. Mass is just the stuff of the universe, atoms, basically. And collections of atoms have gravity. Even a single atom, of course, has a force of gravity, but if it's charged, its electrical force is trillions and trillions of times stronger. So gravity is just a property of matter, and it just scales with matter. The force of gravity in Newton's gravitational law is just a product of the masses of the two particles involved, or two moons, or two stars, or two galaxies, whatever they are. So that's a fairly simple conception. In Einstein's conception, gravity is a little different, because the force of gravity, or rather the motion of objects in space-time, is a property of the curvature of space-time, and the curvature of space-time is determined by the mass energy in space-time. So the amount of mass and energy, the two being related by E equals mc squared. So in Einstein's theory of gravity, it's a geometric theory of gravity where the presence of mass and energy curves space-time, and objects move in response to that curved space-time. So they follow trajectories through the curvature of space-time. And that's why light bends, and there's gravitational lensing, and so on, and also why light can't escape a black hole, or is bent close to the gravity of a compact object. So it's a very different conception of gravity. You could argue that it doesn't completely explain gravity. For example, in the standard model of particle physics, gravity travels at the speed of light, the force, and it has an equivalent particle to the photon called a graviton, a spin 2 particle. It travels at the speed of light and carries the force. Nobody's ever detected a graviton, and nobody's ever shown. It's a difficult experiment that people have tried, but no one's ever successfully shown that gravity propagates with the speed of light. A difficult experiment, because you'd obviously have to switch on and off mass somehow to see gravity propagate. So there are mysteries left in the Einstein conception of gravity, but that's a very different conception than the one that Newton had.
All right, our next question from a live viewer is, I want to know more about the recent kilonova effect when two neutron stars collided, and where's the gold now?
Where's the gold? Okay, and this is a big topic, so I'm sort of going to unpack this into a series of questions and distinguish them so we can sort of march through the information, because this is quite a big event in astronomy. So the first question is, what has LIGO actually found to this point? And the answer to that question is LIGO has detected 4 events and a possible 5th. And the way these events are categorized are that 3 of the confirmed events and the 1 possible event, it's possible just because it was weak and below the significance threshold, are black hole merger events. And the fifth one, the most recent one, is a neutron star merger event. So that's what LIGO has found in its several years of operation. Now, most of that several years of operation was at fairly low sensitivity. What's new in the last year, and what was new about the discovery in October, is that the Virgo interferometer was also operating. So Virgo is a European instrument in the Alps, near the Alps. This is very similar in design and construction to LIGO. The addition of a third interferometer, LIGO, remember, is two interferometers with 5-kilometer arms, one in Hanford, Washington, and the other in Livingston, Louisiana. So the addition of a third detector meant that the localization of the direction of origin of the gravity waves is much better. And so for this fifth event, the localization was better than for any of the previous events. So that was one unique aspect about the recent discovery. And the second, of course, was that it was a fundamentally different type of event. It was a neutron star merger rather than a black hole merger. So the next question is, what was special about this recent event? And what was special about it was that it was an event that had a visible counterpart. The first LIGO detections, black hole mergers, were the mergers of sort of invisible objects. Black holes don't emit radiation, light and radiation, and all particles are trapped inside, and that doesn't change when two black holes merge. So really the only signature of the first three LIGO events were the ripples in space-time propagating at the speed of light and traveling in all three cases for hundreds of millions of years to reach the Earth. So pretty much all you got out of those first three events was the LIGO detection itself. And that was good enough to show that the black holes were massive, surprisingly massive, in most cases, a few tens of solar masses, which is more than the masses of most black holes expected in theory. So that was a surprise. Remember, a black hole in theory is the remnant core of a massive star, which has a mass of a little more than 3 times the mass of the sun. And none of the black holes found in the first three events, the individual black holes that then merged to make black holes with the sum of the masses, minus some mass that's irradiated in neutrinos, were anywhere close to that lower limit. They were much higher, and that was a surprise. So what was different about the new event, the fifth one, fourth if you're ignoring the marginal detection, is that neutron stars, when they merge, produce extreme astrophysics that leads to radiation across the electromagnetic spectrum. So the next question, I'm trying to unpack all this because there's a lot of activity in the last few weeks over this. The next question is, what did we learn from the fifth LIGO event, the most recent LIGO event? So the signature of the merger, just from the LIGO detection and Virgo detection itself, is confirming that it is neutron stars rather than black holes, because the gravity wave signature of neutron stars colliding is quite different from black holes colliding. Remember, the gravity, the size relative to their mass, rather the density of a neutron star is substantially lower than a black hole. So the intensity of the gravitational waves from black hole mergers is higher than neutron stars. Also, neutron stars are smaller than black holes. They're less massive. They're just a couple of times the mass of the sun, as opposed to a few dozen times the mass of the sun. So in those senses, the neutron star merger signal it would make a weaker gravitational wave signature. But this event was only just over 100 million light years away, as opposed to a billion light years away for the first three LIGO events. So it being closer meant it was proportionally stronger and within the range of LIGO detection. So it was a longer signal, a longer gravitational wave signature. It was a weaker signal because the objects are less compact and less dense and less massive. And it was a closer event, 10 times closer than the black hole mergers that were seen in the first wave of LIGO detections. So the next question is, what was seen that was special about this neutron star merger? Well, the neutron star merger creates extreme astrophysics of various kinds. It is a particle accelerator in a sense. And so when neutron stars merge, they send out a flood of particles which in turn can accelerate and heat up any gas that's surrounding in the situation. And so they create a blast wave, a shock wave, and an extraordinary radiation signal. And so the neutron star merger led to two things that were seen. One was seen by satellites and the other by ground-based telescopes. Led to a gamma ray burst, the moment of coalescence of the neutron stars. The extreme high energy radiation makes a short pulse of gamma rays, and NASA satellites were able, where they could look back through their records on that part of the sky and see the gamma ray burst. So they have now definitively attached a gamma ray burst signature to colliding neutron stars. There have been speculation as to what gamma ray bursts are. Several thousand have been known from gamma ray satellites over the decades. Some of them may actually be supernovae or hypernovae, single stars dying violently, but it's now really important to know that neutron star mergers can make a gamma ray burst. The kilonova effect is the part where you actually generate enormous amounts of electromagnetic radiation at lower energies, so optical, infrared, and even radio waves. And kilonova implying that it's about 1,000 times more luminous or more energetic than a supernova, a single star exploding. And so that high energy radiation, that enormous amount of radiation across the electromagnetic spectrum was picked up by dozens of telescopes. For example, the larger telescopes were able to see the fading afterglow of the gamma ray burst as the radiation propagated down to lower energies like infrared and optical waves. Other telescopes were able to see the galaxy within which this neutron star merger came. And so the galaxy is known. And that is extraordinary because the three black hole mergers are not localized on the sky very much at all. I mean, a big swath of sky is up for grabs. So there's no way to say what astrophysical object these black holes were embedded in when they merged. Whereas the neutron stars, we know exactly what object they were in, and we know exactly how far away it is. And so we have a lot of information about this neutron star merger, where it occurred, how far away, how long ago, how much energy, how it relates to gamma ray bursts and other energetic phenomena. And so it's been a sort of gold mine. And the general term that's now been coined for this kind of phenomena is multi-messenger astronomy, where the messenger of gravity waves is very important and sort of unique information, only available in the last few years. But when you couple the gravity wave information with a rich harvest of electromagnetic observations, I think over 70 telescopes were watching this one event in a few week period. That's an incredible trove of data, and astronomers have published reams of papers on this in the last month. And then the other question that comes up is, what about the heavy elements from this recent gravity wave event? So you've probably seen statements in the popular press, and they come from scientific sources, so they're fairly accurate about, I've seen numbers that vary by an order of magnitude, which probably relates to uncertainty in the models, of something like 20 to perhaps 200 Earth masses of gold or platinum produced by these neutron star mergers. That is a phenomenal number. I think I did the math and tweeted this a week or so ago. But if you take that gold harvest from this single merger event and turn it into, current price of gold, it's 10 to the power $31 worth of gold created in basically a fraction of a second, a blink of an eye. It's pretty phenomenal. Now this is exciting in its own right. First of all, why do you get heavy elements out of a neutron star collision? That's not an obvious outcome. And the answer is because when the neutron stars collide, not all of the neutron material, remember neutron stars are pure neutron material at the density of the atomic nucleus. They're like an enormous, you can think of a neutron star as an atomic nucleus with an atomic number of 10 to the 57, because that's how many neutrons are in it roughly. When those neutron stars collide, not all of the neutrons go into the merger product. Many neutrons are released, enormous numbers are released, and they're released at extremely high energies just because of the energy of the collision, relativistic energies. Those neutrons impregnate atoms in the surrounding medium, and they do so very efficiently because neutrons, of course, have no electric charge. So if there's an existing heavy element, just say the nucleus of carbon or nucleus of of iron or nickel or any of the sort of medium mass elements in the periodic table, then those neutrons will penetrate the nucleus and ratchet up the atomic number. Now, the reverse beta decay will take place, and the neutron can turn into a proton, and so that's how you go up by one atomic number. And so there's a mechanism through neutron capture to create all the elements in the periodic table, up to uranium and including all the precious elements, gold, silver, platinum. And so that's where that headline comes from. And it's an extremely efficient process using neutrons. And so people are not yet sure the final numbers. But this is sort of transforming our standard story of where the heaviest elements come from. In the traditional astronomy jargon, there's two processes for heavy element production. There's an R process and an S process, and that just means rapid and slow neutron capture. The rapid neutron capture happens typically in a supernova, a single star dying, and the slow neutron capture can happen in the envelope of massive normal stars. Doesn't actually need a superviolent event at all. The neutrons are there and they can just impregnate the nuclei of atoms. This new pathway of neutron star capture, because it creates so many high energy neutrons and it's so efficient at creating heavy elements, potentially accounts for the bulk of the heavy elements. People are basically arguing about the details. But even though neutron star collisions are rare, they release so many neutrons that this could account for a significant fraction, perhaps the majority of all the gold, silver, platinum, uranium atoms in the universe. So it's a very exciting idea that this event that's just been detected for the first time could transform our notion of where heavy elements come from.
So we have a few follow-up questions about gravitational waves. So this one, I think I understand what they're asking, but the question is from Steve, who's on with us live, who asks, could gravitational waves, if strong enough, be felt here on Earth? And I think he means by a person without an instrument.
Right.
But we can talk more broadly.
Sure.
Too.
The short answer is no. The detection of gravity waves, that is the most precise physics experiment ever constructed by orders of magnitude. If you took physics as an undergrad or looked in physics textbooks, you probably know that there's a nuclear resonance method called the Mossbauer technique that is traditionally the most precise physics experiment. Its precision is about 1 part in 10 to the 16 or so. That's also the precision of the best atomic clocks, as a coincidence. The precision of LIGO in absolute terms, which is to say as a fraction without units, is about 10 to the minus 21, 1 part in 21. So LIGO, just put simply, was the most sensitive physics experiment of all time, is the most sensitive physics experiment of all time by a factor of 100,000. And what it means is this is an instrument that uses enormous path lengths of light being reflected through evacuated cylinders to measure slight changes to a test mass caused by the passage of gravity waves. And those slight changes, essentially, think of the gravity wave compressing and then rarefacting not just space, but matter itself as it passes through matter. And so squeezing and unsqueezing matter by a small fraction of the width of a proton, at about 100th the width of a proton. So you need an enormous instrument and phenomenal sensitivity to detect this very slight compression and rarefaction caused by a gravity wave passing through matter, the Earth, our bodies, everything, anything, by that incredibly tiny amount. So when you know that the amount is that tiny, not just smaller than the atom, but smaller than a proton, then you can understand that we could never possibly detect this ourselves. It's needed an instrument that costs hundreds of millions of dollars to detect these incredibly tiny effects, which is why many people thought it would never happen. Many people thought Einstein's prediction of gravity waves would literally never be tested.
The next question is from someone who's on with the slide, who asks, if gravitational waves travel at the speed of light, how are we able to respond to the detection with optical telescopes in time to see anything, to see the merger?
So that's a good question. The gravity waves, of course, originated in this event. I think it's 130 million light years away. So they They were emitted 130 million years ago when, before the extinction of the dinosaurs, when the big lizards ruled the earth and there weren't even any precursors to apes and humans. So a very long time ago, they've been traveling through space for that length of time. And then eventually they sweep through the galaxy and across the earth. So the electromagnetic signals are essentially traveling at the same speed. The gravity wave pulse, of course, reflects the instant of the merger. I mean, the crescendo, it's called a chirp because you can convert the gravity wave signature into equivalent of a sound because the frequency of the ringing as the neutron stars spin faster and faster in their death spiral goes through frequencies of tens up to hundreds of hertz. And so it's called a chirp. You can imagine it as a sound, but the crescendo, the spiking of that chirp, is the actual coalescence itself when the two objects have fully combined. And then there's just some ringing, some leftover ringing. So that was what the instrument saw. But the enormously powerful astrophysics that results from the merger plays out over little longer timescales because that energy, of course, leaves the scene, the scene being two neutron stars, each of which are smaller than a city, and they've combined to be an object that's still smaller than a city. And that radiation travels out at close to the speed of light, and the particles are relativistic too, so almost the speed of light, into larger regions where a lot of the energy is deposited. So that takes a little longer because the light travel time through a solar system region would be hours or maybe a day, and then beyond that, days and weeks. And so because of the third interferometer, the Virgo interferometer, the gravity waves were localized on the sky much better than had been done for the first three black hole mergers. So astronomers of various kinds knew roughly where to point their telescopes. And so it was then fairly easy for them to look for the afterglow of the radiation being dumped into the region of space around the neutron stars. And as soon as the first telescopes had seen the afterglow, and these were quite small telescopes actually, so there are very rapid response small optical telescopes that locked in on this region of sky. Once LIGO put out the alert immediately, of course, a worldwide alert. And so there were optical telescopes pointing in that piece of the sky literally within minutes. And within an hour or so, they detected the fading remnant. It wasn't, I don't even think it was fading at that point. The afterglow faded for days and then weeks. And the gamma ray satellite, the other NASA satellites were able to point at it also almost immediately, because when the optical counterpart was found, you had it localized in space extremely accurately, much better, much more accurately than the gravity wave initial signal. So basically, with these very rapid response networks, which were set up not for gravity waves, but actually set up for things like gamma ray bursts and supernovae and other violent events in the universe. So astronomers have been building their capability in this regard for a few decades. So when a gravity wave is localized, as it was because of the addition of the Virgo interferometer, they are on it and they are able to find the counterpart very quickly. And like I said, something like 70 telescopes in the end were able to observe it in various different ways. So this is now expected to be routine, and this is multi-messenger astronomy. This is now the beginning of a new era of astronomy where the gravity waves detected by LIGO, which are anticipated at a rate of about one a week of various kinds of events, will all be able to be followed up by other telescopes.
All right, next question is moving on a bit from gravity waves. Leilani asks, is the Higgs boson responsible for shaping the cosmic filaments in the universe, or is it dark matter?
The Higgs, distinguishing these is important. The Higgs boson or Higgs mechanism, it's almost a mechanism rather than a particle, is the method by which in the standard model of particle physics, mass is attributed to particles. So, people have wondered in a very fundamental sense, where does mass come from in the universe? Why is the mass of the electron 2,000 times less than the mass of the proton and the neutron? And then there are other fundamental particles with other different masses. Where does mass come from? So the Higgs mechanism attributes mass to all particles, including the hypothetical dark matter particle, which in the best guess is a supersymmetric twin that comes from the unification of fermions and bosons in some supersymmetric particle theory. But all of those particles in these supersymmetric theories are still getting their mass from the Higgs mechanism. So that's all the Higgs mechanism is. It's a method for attributing mass to any fundamental particle. As for what causes the filamentary structure in the universe, that is indeed mostly crystallized or facilitated by dark matter, because dark matter is the dominant mass component of the universe. And on those very large scales, the dark matter is mostly smooth, but it, of course, is subject to gravity. That's the force it is subject to, since it doesn't participate in electromagnetic interactions. And so over time, this doesn't happen quickly, but the universe is 13.8 billion years old. So over time, over billions of years, the dark matter does clump steadily and slowly by gravity. And it clumps not just in a spherical sense of forming blobs, spherical blobs, and falling in radially, but it also collapses in along different dimensions, one-dimensional strings, two-dimensional sheets, or possibly in a symmetric three-dimensional sense that produces a spherical concentration of dark matter. So the filamentary structure we see in the universe is indeed a filamentary structure of dark matter. And you can see computer simulations which only include dark matter. They don't include normal matter, where they color code. Dark matter, of course, doesn't emit light, so you have to just use some color code in the computer. And typically they color it some red color because it pops out against the black background. And that gorgeous filamentary structure you see in any dark matter simulation is a reflection of gravity operating on dark matter over billions of years. And if you trace the time evolution of the simulation, you can see that filamentary structure essentially crystallizing over time as you play the simulation forward. It's beautiful simulation work, and it seems to be accurate because it does reflect the concentration of where we see visible matter in the universe as well.
Right. The next question is from a live viewer who asks, how do you feel about the fact that private companies such as SpaceX seem to be outranking governments in terms of space exploration and discovery?
Well, I don't feel bad about it. NASA's not going out of business anytime soon. NASA still has an $18 billion budget, almost $19 billion. And, you know, they have to do a lot with that, but they're still sending some amazing missions up there. Kepler is a good example. We've been talking about that. Hubble entering its third decade. The James Webb Space Telescope going to be launched in about a year. Its launch was just delayed, actually. So NASA's still able to do some pretty impressive things. But of course, NASA has been really bad at getting astronauts into space. It's now over 5 years since NASA was able to put an American astronaut in space. The only American astronauts that have been up in that time got help from the Russians in the Soyuz vehicle. So that's a big black nose, have a black mark on NASA, and that's the void that some of these private space companies are stepping into. SpaceX has not yet launched astronauts. They've been resupplying the space station, and they've been getting multi-billion-dollar contracts from NASA to do that. They are projecting with their current their Falcon 9, their current launch vehicle, the ability to put astronauts up probably late next year, late 2018. That's what they claim. There may be some slippage in that. And so it will be a private company and not NASA that ends this, what will be a 6-year drought of Americans putting Americans into space. And there's no reason to think that'll change. NASA does have a launch vehicle under development, Constellation program. It's morphed and changed and had budget cuts. And, you know, part of NASA's problem is the vagaries of funding and the election cycle that stops them being able to plan on decent timescales. So NASA is going to get back into the game of launching astronauts, but some people are quite critical of their launch system. They think that it'll be technically very competent and it'll be able to carry a good payload, but probably at a much higher price than SpaceX or Blue Origins or a few of the other space players will. So the private companies, because they don't have the continuity of funding and the reliability of a budget from the taxpayer, they have to be more nimble. They have to be more efficient. At some level, they got to pay back their investors eventually. And none of them are turning a profit yet, but they have to have a business plan that says they will turn a profit. And so I think the presence of this private companies is a good thing because they're driving innovation. They're lean and mean because they have to be. They have to be more efficient. They have to be more cost conscious. And sort of they're pushing the pace.
All right, the next question from a live viewer is, if it takes several generations of stars to produce the heavier elements in the periodic table, and many billion years for each generation of star to form and die, how would there be sufficient time for this to happen before the Earth and solar system were formed?
So it's a good question, and the answer is because the answer is how the heavy elements are made, or what kind of stars make the heavy elements. So if you take a star like the sun, which we think of as a typical star, it's not actually the median star, if you like. There are many more dwarf stars than stars like the sun. But it's therefore a true statement that most stars have lives that are billions of years old. And most stars don't make very heavy elements. The sun will make a little carbon, and that'll be the end of the story. And late in the star's life, it'll eject about a third of its mass as a planetary nebula. And so some of that carbon, along with hydrogen and helium and other light elements, will be ejected into space. But the sun won't make the heavy elements like even iron or anything beyond iron. And of course, it's taking billions of years to do so. So if it were just stars like the sun and the even more ubiquitous red dwarfs, which live even slower lives and make even less heavy elements, they can't even make carbon, then the question would be good because, how on earth did we get all the heavy elements in the Earth? But once you look to the most massive stars, take a star that's 10 times more massive than the sun, its total lifetime is, I don't remember the exact number, but it's something like 50 million years. So a star that's 10 times more massive than the sun lives 100 times less long than the sun. And it gets hot enough in its death, in its supernova phase, to generate all the heavy elements. And so the answer is that the most massive stars that formed early in the universe live their lives with very rapid cycles. And so for instance, in a billion years, you could easily have 100 generations of massive stars living and dying and spewing out heavy elements that were then part of the medium that formed the next generations of stars. So you can ratchet up the amount of heavy element in the universe, the heavy element component of the universe, fairly rapidly. It's still a trace component of the chemical composition of the universe because those very massive stars are rare. The star 10 times the mass of the sun is probably hundreds of times rarer than the sun. But the time scale works, so you can definitely generate enough heavy elements to see the heavy elements that we find in the Earth. So by the time the Earth formed, 4.5 billion years ago, there had been plenty of time for massive stars in the galaxy to create heavy elements that would then become part of the Earth, our bodies, and everything around us.
So the next question is from Samira, who's on with us live, who asks, have there been any new discoveries related to life in the universe? Any updates regarding Mars, or what scientists are planning to do to look for life?
I think there's no success. You would be seeing front page headlines if SETI had succeeded. So the search for extraterrestrial intelligence does continue. It's not quite as grandiose as people hope. The Allen array was not fully funded, and so it's working with a fraction of its total number of telescopes. Arecibo, the biggest dish that can be applied to SETI, was seriously damaged in the hurricane a few months ago. So, the SETI is sort of, I would say, limping along, but it hasn't had any successes. All the action in the search for life in the universe involves identifying the nearest Earth-like habitable planets for more detailed investigation. So I'd say that's where the activity is. Because what people are hoping for and aiming towards is an experiment where for a relatively near habitable Earth-like planet, by that I mean 10, 20 light years away, pretty close in the universe, we have the prospect with big new ground-based telescopes and with proposed space-based telescopes to take the feeble reflected light from that Earth-like planet. Remember, it's 1 billion times fainter than the star it orbits. Blot out the star it orbits and use the reflected light of that Earth-like planet and make a spectrum of it and look for biomarkers, which is to say chemical tracers of life, because it imprints in the atmosphere, just as the oxygen and ozone in our atmosphere is a reflection of earlier life on Earth. So that experiment is being planned. People have known that they wanted to do it for decades. The technical capability to do it is very close now, and I would say that the experiment will start to be done in the next few years. James Webb Space Telescope is planning to do some of this work in the near infrared, but was never designed to do this science, so it's not maybe the most efficient way to do it, even though it's a 6.5-meter telescope. So although no life has been found elsewhere, that experiment is on the horizon. Very exciting. Within the solar system, things also move fairly slowly. So the current Mars rovers are just, nailing and sealing shut the case for water on Mars. The fact that Mars was warmer and wetter in the past, had standing bodies of water, and they're also providing good evidence that the water can episodically appear on the surface. It'll evaporate, of course. Mars has no atmosphere and the pressure is so low, water can't sit on the surface. So the rovers and the orbiters are just sealing the case that Mars was wet and warm in the past and water can erupt onto the surface. They're also providing an inventory of the water on Mars. The subsurface glaciers in the mid-equatorial regions of Mars, if you were able to melt all that under ice that's not even very far under the surface, it's just a cap of rock and ice tens of meters thick, and then there's a lot of ice like glaciers. If you were able to melt that, it would form a puddle or sort of pool of water on the whole surface of Mars about 4 centimeters or 1.5 inches or 2 inches deep. That's quite a lot of water for a planet that seems bone dry. So all of that is information from the last few years. But actual detection of life on Mars, that's really not on the horizon for the moment. The twin of the Mars, the Curiosity rover, there's a rover 2020 mission, which was essentially a knockoff or sort of duplicate of the Curiosity mission, because it's quite cheap to just duplicate your hardware when you know it works. That probably won't go there in 2020. It'll be a year or two after that. And it's going to do life detection, but not very sophisticated life detection. It's an incremental step forward. None of these rovers has the ability to drill under the surface to a place where there might be liquid water now, and therefore life now. So life detection in the solar system is going to be a slow business because these missions take decades to plan and launch. So I think, if I were betting, I'd say the first detection of life beyond Earth will happen by the atmospheric imprint of life on a terrestrial planet in the nearby universe within a decade.
Right. Our next question is from Maria, who's on with us live, who asks, do stars change colors in their lives?
Yes, they certainly can, and they do. So the color of a star is, of course, a measure of what we would call its surface. Now, a star doesn't have a firm surface at all. It's just a gas ball where the density, pressure, and temperatures just change smoothly as you move out until it fades into space itself. But what we see is the photosphere, or the edge of a star like the sun or any star, is the place in its outer atmosphere where radiation, having bounced around and reached the surface from a fusion region with a temperature of millions of Kelvin, drops to a temperature of thousands of Kelvin, and eventually the photon will not interact with any other particle, particularly electrons. And so it leaves freely and travels in straight lines at the speed of light, and that's how we see the surface. So the photosphere corresponds to that outer region of a star where the radiation can escape and travel freely. And the temperature it has just corresponds to the mass of the star. So the sun's mass gives that outer region a temperature of a few thousand Kelvin. If you had a white dwarf, which is a very hot, dense star, that outer region, the photosphere, could have a temperature of tens of thousands of Kelvin. And if you had a red dwarf, a very low mass star, cooler star, the temperature of that photosphere or outer region could be a few hundred Kelvin. So that's actually far red, almost going into the infrared. Now, as stars, so that's different stars having different colors. That's a real phenomenon. When you look in the sky, which your eye can just about detect the difference in the color of stars. That's reflecting the different temperatures of their surface regions. As for a star during its life, that can also change its color. For most of the fusion uh, lifetime of the sun, which is almost 10 billion years, it really won't change color. I mean, whatever yellowish color it has now, it had 3 billion years from ago, and it will have 3 billion years from now because it's doing the same thing. Energy output is the same, and so this surface, as we see it, has the same temperature and therefore color. But when stars change their energy source, they reconfigure themselves. They often rearrange themselves. The core collapses, they heat up, the outer parts get hotter. And so you can have a quite different temperature of a star. And indeed, when the sun exhausts its hydrogen source and reconfigures itself, it's going to eject an outer atmosphere that will heat up quite dramatically and will blow it into a red giant. So that the inner part will get hotter while the outer part actually gets cooler. And so from afar, the sun will look red. So typically when stars change their fusion energy source, either when it first ignites or when they exhaust one fusion fuel and go to another fusion fuel, they reconfigure and do change their colors. And so that happens that happens for almost every type of star.
Right, the next question from our live viewer is, at what speed did the universe expand in the fractions of a second after the Big Bang?
So it's a model because we don't have any evidence, direct evidence of that. We measure the precession of galaxies now in the present old universe, 13.8 billion years after the Big Bang, and we can look out in space, and back in time, maybe 11 billion years, but we can't directly observe the recession of galaxies. Obviously, before galaxies existed, there's nothing to measure. So all comments about the expansion rate early on come from the Big Bang model itself. They're just a prediction of the expansion history of the universe. And that prediction, of course, is that in the very early universe, the expansion rate was incredibly fast, and it was much, much faster than the speed of light. To give a benchmark on this, the Big Bang model predicts that at the time of the creation and release of the microwave background radiation, that's what you see when you point a microwave telescope at the sky and see this speckle pattern that are the seeds for galaxy formation and an almost uniform temperature in all directions. That was 380,000 years after the Big Bang. It's a very small fraction of the age of the universe. And the expansion between any 2 points in space at that time was about 40 times the speed of light. So a full few 100,000 years after the Big Bang, the expansion rate between any 2 points in space was 40 times the speed of light. So you can imagine that earlier still, it was even faster. So for most of its history, actually the majority of its history, the universe has been expanding faster than the speed of light. That is, any 2 points in space are moving apart from each other faster than light speed. The subsequent slowing down of the expansion until more recent acceleration due to dark energy allowed the light from these distant regions to reach us. So the universe was essentially expanding at a phenomenally fast rate early on, much, much faster than the speed of light.
All right, so the next question is from a live viewer who asks, is it possible that most of the new theories in physics, like the Standard Model, dark matter, dark energy, string theory, are wrong?
It's possible and even likely in some views by fairly sober-minded physicists that some number of our current theories are wrong. Wrong is a tricky word. You could say incomplete to the point of being conceptually wrong. Newton's theory is not wrong because Einstein came along with the geometric theory of gravity. Newton's theory is an approximation that fails when the gravity is strong, and it's also conceptually very different from Einstein's theory. So Newton will make wrong predictions in situations of extreme gravity, and in that sense, yes, it's wrong. But in the sense of what theory do we use to send spacecraft around the solar system and around the Earth with no problem whatsoever, it's Newton's theory. So that's that's part of it. The new theories don't always blow the old theories completely out of the water. They just expand their range of applicability, and often they have a different conceptual basis. So they feel very different flavor. Like string theory, as a basis for understanding particles, is quite different from a model that thinks of them as little billiard balls. So, in that sense, yes, it's likely that some theories are wrong. The biggest hole in our theorizing is, of course, a theory that unifies the four forces of nature. The most resistant forces to unify are, of course, the electromagnetic weak and strong interactions with gravity, because gravity is so much weaker than the other three that it's in a different regime. And theories of how that works that unify quantum mechanics or quantum, the description of how fundamental particles work with the theory of how gravity works, that has been a long, difficult road where people have not had success. They've had some clever ideas. Um, so nobody really knows what that looks like. Is it possible, again, that some of our ideas are wrong? Yes, it's possible that our ideas about dark energy and dark matter are wrong, and especially dark energy, because we have very little idea of what that is physically, is not really predicted out of any fundamental physics theory. And so, it's possible that that conception of dark energy is just wrong, that we're misled about it. I don't think the data on the accelerating universe is wrong, but the interpretation of that data in terms of of an entity that has negative pressure and so causes space-time to accelerate in its expansion, that just could be wrong. Um, Dark matter is likely to be something that's real in the universe because we see the effects of its gravity in lots of different situations, and we can measure the amount of dark matter in different places on the different scales, and different methods agree on that. So there's something there. But again, as for what it is might overturn some very well established theories of physics, including pieces of the standard model of particle physics. So physicists are theorists, especially who think deeply about these things, they're quite likely to accept the idea that some big chunks of physics are incomplete to the point of being wrong.
Right. The next question is from a live viewer who says, I'm frustrated I can't chart the brightness and period of delta CPI by eye. I can estimate magnitude, but my findings don't seem to agree with its period. Is there a published almanac of its period that I can check against?
It's a good question. It's pretty far from my research field, so I'm not going to be able to give a detailed answer. But yes, I know it is such a notable, famous object, and bright enough that it's subject of amateur professional astronomer collaborations, that it almost certainly has an ephemeris, and there's almost certainly an online database of observations of it from the people who collaborate on monitoring it. So all I can suggest is you sort of drill down on the internet and figure out which research groups have it as part of their monitoring campaigns. And even if their data is not visible in a public archive, they're almost certainly willing to share it, because astronomers, especially on objects where you have to monitor it and where you want to gather data and have people collaborating and doing multi-wavelength monitoring campaigns, they're very open about sharing data. So I suspect even if it's not visible on the web, you'll be able to make a contact that will let you look at their data and establish an ephemeris.
And you can also check the AAVSO,
Yeah.
see if they have anything.
The AAVSO is the American Association of Variable Star Observers, very active, very much a professional amateur collaboration consortium. I think thousands of members, active members, people actually making observations and sharing them. So it's another resource.
All right, and our time is almost up. So one last question from Ryan, who's on with us live, who asks, are there any cool experiments or missions that you would love to see done, but right now seem unfundable or unpractical? Impractical.
Yeah, the one I obviously want to see happen, since I work on, in my research, I've worked on supermassive black holes for a long time, quasars and supermassive black holes and how they grow and how they evolve. What I want to see is the analog of the LIGO experiment that allows you to see massive black holes merging. So we've seen black holes that are 10, 20, 30 times the mass of the sun coming together, creating gravity waves. Well, out there in the universe, galaxies grew by mergers and acquisitions. And when galaxies merge, their black holes merge. And their black holes are 1,000,000, 10,000,000, 100, maybe 10 billion times the mass of the sun. That's the biggest mass black hole we've ever found. And so when those black holes merge, it creates gravity waves with much lower frequencies. They do the same chirping thing. They merge, they send out gravity waves very powerfully, but the frequency of those gravity waves is orders of magnitude lower, and you can't do them from ground-based observatories. There's too much geological noise. So you have to use interferometers in space. And that's the LISA project, the Laser Interferometric Space Antenna. And LISA got some very important good news last year from the European Space Agency. It was approved, it was green lighted as a project for the next decade. But I mean, literally, we mean a decade before they even do they've done some basic engineering and proof of concept. So LISA is the thing that's a very difficult experiment, but with LIGO successful, the motivation to do it is extremely strong. It would open up the gravity wave window of the universe onto the most massive black holes in the universe and what they do. And that's something I'm very excited by. So it's 10 to 15 years off. And that's all for today. So thank you very much for participating, and we'll be back in a couple of weeks.